Okay, in this video, I'm going to work out the last piece of the linear regression example that I have up in Blackboard. So in a couple of videos prior to this, we worked out parts A through F in this example. This last part, part G, asks us about residuals. So let's give a look here. So it first asks us to create a residual plot. Now, in JUMP, that's really just kind of the click of a button. Once you have the linear fit all set up, and remember we did this in a prior video, all you need to do is click on that little button right there, and somewhere down here we go, plot residuals. If you click that, it creates a residual plot, and it creates several residual plots. Just to give you a reminder of what residuals are. Residuals are the difference between the predicted and the actual Y values. In other words, when we created this model, this sales model here, remember this was a predicted sales, but remember they were actual sales from data that was collected. If we use the model to predict for 5.5, get that value, and see the difference between that predicted value and the actual value of 100, what's the difference? Remember, it's kind of like an error factor. The difference between the actual and the the actual and the predicted, that gives us the residual. And if you do that for all these values, in other words, use the model to predict what the actual sales would be, subtract the real sales values, we could create residuals here. Now, believe it or not, JUMP did that already. And in here, there's a little command that says save residuals. So if I click that, what it does is in the data table, it dumps in all the residuals. So in other words, if you look at the first residual, which says negative 5.09 approximately. Now, what does that mean? Well, remember, the model will predict for 5.5. In other words, if I take that 5.5 and plug it into the advertising cost, it'll obviously work out the predicted sales. So if I look at that, 28.645753 plus 13.899614 multiplied by that given X value of 5.5. So if I hit enter, the model predicts 105.09363. Now the actual value is 100. So if we take the actual value, 100, and subtract off that predicted value, there you have your residual, negative 5.09363, and as you can see, that's this value here. Do that for all such values, and there's all your residuals. Okay, so the residuals are pretty easy to calculate. Now, when I went to this little red triangle here and asked JUMP to plot the residuals, and it took care of it for me, it created several residual plots. You have predicted sales versus the actual residuals. The one we're looking for, though, is this one here, the residual by X plot. What this does is it plots the actual X values, the advertising dollars, and then the residuals. So in other words, if I went back to the data table, the actual X is here, advertising, and then these residuals that are calculated, it graphs the X versus the residual, and there you can see it. Now, what we're really looking for is a couple of things in the assumptions. Remember, the assumptions, when we looked at them in this chapter, there was a few of them. First of all, the residuals, remember, are scattered randomly and independently. So if you look at the scattering of the residuals, as you can see, there's no clear pattern to them. Also, there was a variability assumption that there was a constant amount of variability. So if you look at the distance, from here, imagine a straight line going across here and down here, the data scatters equally pretty much throughout this. Now, don't forget, this is only an example from a textbook that only has 12 pieces of data in it. The reality is this is a model problem from the textbook, and having only 12 pieces of data naturally doesn't make it so real world. But imagine there were thousands of values in here scattered throughout, and the data was, scattered pretty evenly. In other words, we don't have something, like this going on where, the residuals are scattering and getting, more and more spread out as X increases. That would be some type of heteroscedastic scenario where the amount of variability is changing throughout the residual plot. If you look at the one that we're working on right now, it here's the 0 line. The data kind of nicely scatters, and there's a constant amount of variability between the data. Now again, if you look at this picture, it's not perfect, but once again, it's only 12 pieces of data. But this doesn't have some kind of real bizarre scenario where I would want to say that this is heteroscedastic, and then that would violate our assumption of variability there. In addition, I see the randomness of my scatter. I do see a couple of possible outliers, like this guy right here. That value is a little low, as is this guy. Is that going to make us throw out this linear model? Not right now. You would need something would need to be drastic in order to do that for this scenario. So what we're really looking for in this residual plot right now is the fact that the data is randomly scattered about 0. And if you're wondering, why is it scattered randomly about 0? Well, remember, if you sum all the residuals, you'll get 0, which naturally makes sense that they scatter around 0. So the mean would be 0 there. And then the residuals should randomly scatter throughout that scenario. We shouldn't have any kind of, trumpet effect where this looks like the end of a trumpet or a bugle. That would mess up our constant variability assumption. And then we shouldn't have some, curvature in our data. And as you can see, the residual plot doesn't show any curvature in the data. For that to happen, we would need to have a residual plot that did, something like this. If here was the 0 line, if the residuals, trended and did something like this and then came back up again, showing you some kind of curvature in your data, it would magnify the curvature. Maybe the curvature wouldn't be so obvious in the original scatter diagram, but the residual plot would magnify that. As a matter of fact, that's the residual plot does. It magnifies this scenario here of heteroscedasticity. It magnifies nonlinear trends, and it would magnify the variability assumption, obviously. All right, so when I look at this residual plot, I noticed a random scatter, and I don't see any big violations going on here. Again, I do have a little bit of a weariness about these outliers here, or possible outliers, but not one that's going to make me throw out this entire linearity assumption. All right, so hopefully this helps you out. If you have any questions on this, feel free to shoot me an email. Thanks for watching.